In this video we discuss quantitative aspects of bond energies, and we see a recipe to calculate the energy exchanged in a reaction by using the energies of the bonds that are involved in the reaction. Right, let's think about a diatomic energy diagram, which is like this. Okay, what we're trying to map here is how the energy of a diatomic molecule changes with the distance between the two atoms. This is going to be a generic molecule XY. Okay, so we have here X bonded to Y, and again this is generic. And we've seen these diagrams before. What we know is that if X and Y are sufficiently far apart, the distance between them is large, then they will not be interacting. Okay, so the energy looks like this at very long distances between X and Y. But as soon as X and Y come within some critical distance, then the electrons of X will be attracted by the nuclei of Y and vice versa. And those interactions start stabilizing, which means that the energy drops. Okay, the energy will drop until you get to the maximum attraction, which is the equilibrium distance. And then after that point, if you try to push the atoms closer, what will happen is that the protons of atom X will repel the protons of atom Y, and that will give rise to a rapid energy increase, which we can plot like this. Okay, so again, notice that if you're infinitely separated, your energy, we will call that 0. And then down here, that is where the molecule is most likely to be, at least in a classical sense, and therefore the difference in energy between these 2 points is what we call the bond energy. Okay, we're going to call the D as bond energy. Okay, so for typical bond energies are, for example, something like this. For H2, this bond energy is 432 kilojoules per mole. For Cl2, we have here an energy of 239 kilojoules per mole, and if the molecule is HCl, the energy is equal to 427 kilojoules per mole. Okay, so these are sizable. These are ways to quantify typical bond energies that you find in diatomic molecules. Okay, notice that in all of these molecules, we're actually looking at covalent bonds. Okay, these are pure covalent bonds, 100% covalent bonds. That is a polar covalent bond, HCl. Okay, so you have a covalent contribution, but also a little bit of an electrostatic stabilization from the fact that H is partially positively charged and chlorine is partially negatively charged. Okay, but again, and bond energies on the order of a few hundred kilojoules per mole are typical in most bonds. There should be a dependence on whether the bonds are single, double, and triple, and that is very well seen when you look at the bond energies of CC single bonds, CC double bonds, and CC triple bonds. For example, the typical CC single bond is about 350 kilojoules per mole. The typical CC double bond is about 600 kilojoules per mole. And then when you go to a triple bond, triple C carbon-carbon bond, that energy is on the order of 840 kilojoules per mole or so. Okay. Now, something that is very important to understand is that when the bond is formed, okay, that energy is released. Okay, it's a stabilization, and that energy is released. In chemical terms, we say that that energy is negative because it's being given off by the formation of that molecule. Conversely, if you're right here and you need to break those molecules, those atoms apart, if you need to break the bond apart, then you need to supply energy. Okay, so from that perspective, the sign of that energy will be positive. Well, so it turns out that we can actually use these bond energies to calculate the energy of a reaction by simply tracking how many bonds are formed and how many bonds are broken. Right, so we can clearly see that if we now look at the reaction of H2 plus Cl2, hydrogen and chlorine to give 2 molecules of HCl, and all of this is in the gas phase. Okay, there will be some energy exchange during the reaction. Right, it's quite possible that the energy might give off, that the reaction might give off energy, or it may be possible that we actually need to supply some energy in order to go from reagents to products? Well, it turns out that there's an easy way to calculate the energy involved in that reaction by just tracking the bonds that are being formed and broken. Okay, when we look at H2, we can say that, well, H2 is a molecule with a single HH bond, and then Cl2 is a molecule with a single Cl-Cl bond, and then when we go to HCl, that molecule is simply HCl, okay, with a single bond. Okay, so what we have here is that the reaction involves the breakage and formation of covalent bonds. Okay, notice that you need to break an HH bond, you need to break a Cl-Cl bond, and then you actually are forming a HCl bonds. Okay, so if we go back to the argument of what gives off energy and what needs energy, breaking bonds needs energy. So we have to supply some energy in order to be able to break these bonds. Conversely, making bonds releases energy. Okay, so here we'll have the energy released by the formation of two HCl bonds. So the total reaction energy will be just the balance of the energies of the bonds that are broken and the energies of the bonds that are formed. Okay, we can actually write that down using an equation that is very simple, right? The energy in a reaction, okay, is simply going to be equal to the sum of the bonds energy, the energies of the bonds that are broken, minus the sum of the energies of the bonds that are formed. Okay, again, notice that here we have a positive sign, and that's because breaking bonds requires energy, that is a positive energy, and then making bonds, forming bonds, releases energy, which from the perspective of chemistry, that is a negative energy. Okay, so we can actually apply this expression to this particular chemical reaction with the numerical values that we have for the bonds of HH, Cl, Cl, and HCl, and then figure out what is the overall reaction energy. Okay, so for this reaction, what we'll have is that the broken bonds are HH and Cl, so that is going to be the energy of the HH bond plus the energy of the Cl-Cl bond minus twice the energy of an HCl bond. Okay, so if we take the numerical values that we wrote before, okay, the energy of an HH bond is 432 kilojoules per mole. The energy of a Cl-Cl bond is 239 kilojoules per mole, and then the energy of an HCl bond is 427 kilojoules per mole. Okay, so you calculate that and you find that this is equal to minus 183 kilojoules per mole. Alright, so again, this is a recipe to calculate the reaction involved in, the energy involved in a reaction. The most important aspect of all of this is that the sign that we get out of this particular reaction is negative. That means that the reaction is thermodynamically favorable. Okay, so making this reaction happen will actually release energy, okay, to the surroundings, and the amount of energy released will be equal to 183 kilojoules per mole. That negative sign again means released. The consequence of that, or the origin of that release of energy, is the fact that the bonds that we're forming, okay, HCl, are on average stronger than the bonds that we formed. Okay, so if you form stronger bonds than you're actually breaking, okay, what that means is that, well, there's much more stabilization in products than you have in reagents, and again, you're getting increased stabilization, and that releases energy. Okay. Right, a couple of final considerations here before we finish the video. First of all is that we're writing energy here as H, and we will actually learn when we study thermodynamics that we actually don't talk about energies, we talk about enthalpies, and there's not a lot of difference between enthalpy and energy. Enthalpy is very close to an energy, but we'll have to take some time, again, when we study thermodynamics, to differentiate between enthalpy and energy. For now, we'll simply write enthalpy, and we'll just have the knowledge that thermodynamic variable is very similar to what we consider to be an energy. Okay, that is the first thing. The second thing is that when you go to tables and look for bond energies, there are some limitations to the values of those energies. For one, the bond energies that you find in tables are for the gas phase. Okay, so you will not be able to study reactions involving covalent bonds in the solution phase or in the solid phase, right? You will be constrained to the gas phase. The second thing that happens is that many of the bond energies that you have in those tables correspond to average bond energies. Okay, and we can illustrate those average bond energies by looking at various OH bonds. All right, so for example, think about the OH bond in water, okay, where you have O, H, and H. Okay, the energy of that bond versus the energy of the bond in hydrogen peroxide. Okay, that bond, or maybe the energy of that bond in a different molecule like methanol. Right? Notice that in these three molecules you have OH bonds, right? But we know that the energies of each one of the bonds are actually slightly different. They're not exactly the same. Yet, when you go to bond energy tables, you will find just one energy for an OH bond, right? So it turns out that that energy that you find in the table happens to be an average of a variety of bond energies coming from different molecules. Okay, so while those bond energies will be very useful and very convenient to calculate reaction energies, they're always going to be rather approximate because they correspond to average values. And again, the other limitation is that they have to be in the gas phase. Okay, so in this video, we have taken a quantitative look at the energies involved in bond breakdown, bond formation, and we've seen a very easy recipe to get an estimate for the reaction energy that happens when you have some bonds breaking and some bonds forming.